Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy and honored to have Professor Clifford Taubes with us. He is a William Peschke Professor at the Mathematics at Harvard University. He has made many important contributions in gauge theory, differential geometry, and low-dimensional topology. Among his most influential contributions are the Taubes-Gromov invariant and the Bott-Taubes polytope. The study of geometrical aspects of cyber-Witten theories, and as well as the geometry and moduli space of four-dimensional manifolds. Taubes have received numerous awards, including the Webel Prize, the Clay Research Award, the NAS Award in Mathematics, and the Shaw Prize, and has been 4-time invited speaker at the International Congress of Mathematicians. If you have studied differential geometry, and in particular gauge theories, it is very likely you have ended up reading one of his papers or many of his papers and books on the subject. So today we are with a total authority in the field. Please remember to raise your hand at any point if you have any question, and I will leave you with Professor Clifford. Please go ahead.
Okay, thank you. What I want to talk about today is four dimensions and what we know about four dimensions and what we don't know about four dimensions. And so, the observable universe is four-dimensional. I mean, of course, there are, popular theories that speculate about higher dimensions, but in any event, even in those, you have to end up with something four-dimensional that we observe. So there's a mathematical question, which is what are the possible four-dimensional spaces? Which is related to the physics or astronomer question, which is what is the particular four-dimensional space at our universe? So I want to address the mathematical question, which is what do we know about the possible four-dimensional spaces? So before I go into that, I just want to make a note on that there's a lot of people who work on this, and in particular, this little thing down here. Just on Monday, Ciprian Manolescu, who's a mathematician at Stanford and a very well-known mathematician studying four-dimensional spaces, actually posted an expository paper on the Math Archive, which covers in much more detail and a lot of what I'm going to say today. Okay, so let's go. So we need to understand some terms. So terminology is I kind of like to say that mathematics is one of the few endeavors in life where you actually are supposed to know what you're talking about. And so we have to really understand what do we mean by space, what do we mean by dimension, and what do we mean by listing all the spaces. So those are, in some ways, obvious English words, but they have many different interpretations. And if you're not careful, you end up with the wrong answer. So when we talk about spaces, we have to talk about the local structure of a space. And the local structure is that we want the space to be flat and featureless at small scales. I mean, that's kind of the go-to model. Now, whether that's true at the Planck scales, I mean, nobody knows, but in any event, for all realistic scales, you want it to be featureless, which is saying that you want it to be modeled on a Euclidean space. So that means the real line, the plane, three-space Rn, which is n-dimensional Euclidean space. So those are the fundamental local models. And so they're, distinguished. One point is same as any other, and one direction is the same as any other. And so there's a technical definition if you read the books. The manifold has to be what's called a Hausdorff space, which is a technical thing to rule out some pathologies. But the basic rule is that each point has a neighborhood which is modeled by Euclidean space. It should be the same dimensional Euclidean space in each for each point. So that's the technical definition of a manifold. Now, the dimension of the manifold is the number of that Euclidean space dimension, the number of local coordinates that you need to distinguish any 2 points. So, for example, if you have a circle like the edge of a clock, you just need to tell you where the big hand of the clock is. You just need one dimension. The surface of the Earth is an example of a two-dimensional manifold. So this is a drawing of the Google Earth of the Science Center at Harvard. And if you want to know where I am right now, I'm in that room there. The surface of the Earth is two-dimensional. You have to give the coordinates. We give latitude and longitude, so it's like 42 degrees, 22 minutes, and 35.09 seconds north latitude, and 71 degrees, 7 minutes west longitude. So that would tell you where on the Earth that building is. Now, the Earth is a sphere, so we could sort of, but it's an example of a manifold because it's locally flat. So of course, I suppose people a long, long time ago thought the Earth was flat. The Greeks and presumably before them, people before them knew it was a sphere. And there's actually a very interesting book, which if you have some spare time, I urge you to read. But there's a Greek scholar named Gemino who was essentially equivalent of a college professor or something, who wrote a book called The Introduction to the Phenomena. And there's a really nice annotated translation by Evans and Berggren about that. But anyway, in the book, he gives 3 reasons for coming to the conclusion that the Earth was round. And the first of his reasons is that if you looked at the shadow of the Earth on the moon, the shadow is curved. So you can see that, maybe it's a disk, but anyway, you can see it's not. You can see the roundness in the shadow on the moon. The other, more famous is you can look at the angle the sun makes with a vertical stick in the ground at noon at different latitudes. And in fact, this was how the radius of the Earth was calculated in 2,000 or 3,000 years ago, 2,500 years ago. And then the third reason, which I thought was the cleverest of them all, is that if you go, Gemino taught in Alexandria, which is now in Egypt, North Africa, and if you go west from Alexandria, you see elephants. Famously African elephant. Well, this African elephant is over here. And if you go east from Alexandria into Persia and India, you see elephants. And there are no elephants in the middle. So Gemino made the conclusion that it has to be connected around the back because there are elephants on one end and elephants on the other and none in the middle. So I thought that was actually totally brilliant deduction. Of course, it isn't quite correct, but still. Anyway, so those are the 3 reasons. Now, in fact, we actually need, we live in a 3, we actually need 3 numbers to tell where I am, because if you came to the Science Center, you would have to know what floor I'm on. I'm on the 5th floor, which according to Wikipedia is about 22 meters above sea level. So you need a third coordinate. And then, well, we've exhibited actually the fourth coordinate already because you need to know what time the lecture is. And I guess there was a screw up in the fourth coordinate this morning. So we don't, but so anyway, we need four coordinates to specify an event, and that's why we're four-dimensional. Now, an important point, which I'm sure you're aware of, is that you don't require that the single coordinate chart cover the whole space. And in fact, we know that, for example, the circle can't be covered in a one-to-one fashion by a single chart. You need at least two charts here to cover the circle. So if you try to cover it with one chart, there's going to be an overlap. And so it won't be one-to-one. You need two charts. And of course, well known, you can't cover the surface of the Earth with a single chart because, for example, longitude is meaningless at the North Pole. And if you take a Mercator projector, this is an equal latitude and longitude are now a square grid. You see Greenland looks huge, which is, and there's a political comment I can make, but I'll refrain from making it. Okay, so when you have more than one coordinate chart, you need to make be specific about what you require about their intersection. So here's where things get subtle. Where two charts intersect, the first chart, their intersection is on the one hand a region in the first Euclidean space for the first chart, and on the other hand it's a region in the second Euclidean space in the second chart. And so you end up with an identification between two regions in Euclidean space. That's the region in the first, where the intersection is, and the region in the second. And so the coordinates in the first region then become functions of the coordinates in the second. And then the question is, what do you want those functions? How do you want those functions to behave? So, so the minimal requirement, of course, which is what you need for manifold, is that that's just a one-to-one continuous identification, and inverse is continuous. But if you're going to, but you could require more, and one of the requirements, which is what we're going to talk about, is requiring that those what are called transition maps between charts are infinitely differentiable, or at least differentiable. And the reason you want to require them to be differentiable, I imagine if you're doing physics, is that the laws of physics, Newton's law, Maxwell's equation, Schrodinger's equation, Einstein's, general relativity, all the sort of equations of physics are equations that take derivatives. So if you're going to take a derivative, you need to know that a function which is differentiable in one coordinate chart is actually also differentiable in the other one. So you need to require that the transition maps between the charts are differentiable, and that turns out to be a non-trivial requirement once you get above dimension 3. So we're going to return to that momentarily, but that's a kind of a key point in this whole business. Now, of course, you can require more than differentiability if you're interested in doing, complex holomorphic functions. You would require the transition first charts to be holomorphic, and then you're doing complex holomorphic geometry. Okay, but anyway, but the point is that there's no local distinction between two manifolds of the same dimension, so the distinction becomes a global one. So that's what we mean when we talk about listing manifolds. What is the global properties of these manifolds? So if we go to zero-dimensional manifolds, a zero-dimensional manifold is just some finite collection of points. We have 1 point, 2 points, 3, 4. Each point is only member of its local neighborhood. It doesn't have any local neighbors. So this brings up an important issue, which is the manifolds can be disconnected. And so I'm just going to talk about connected manifolds here because disconnected manifolds are just many copies of a connected manifold. But in practice, and I'm looking at a paper this morning on the math archive or physics archive about quantum gravity in 3 dimensions. Of course, you have to consider disconnected cases. But anyway, 2 disconnected manifolds are just 2 connected manifolds that are attached. All right, so zero-dimensional is easy. One-dimensional is also easy. There's 2 one-dimensional manifolds. There's the circle, which is bounded, and then there's the line, which is the unbounded case. So those are the only 2 one-dimensional manifolds. And so this brings up a second issue, which is manifolds can be what are called compact or non-compact. So, compact, you want to think of it as, you can't escape to infinity, and non-compact, you can. So the circle is called compact, and technical definition is that if you have any sequence of points on the circle, there's always a subsequence that converges. Whereas you could have a sequence of points on the line which just keep moving off to infinity, so they wouldn't converge. So that's the technical distinction. And I'm going to restrict attention to compact manifolds because non-compact manifolds, first of all, they can become quite pathological because you can require all kinds of basically awful behavior as you go farther and farther out. Of course, you could restrict the behavior far away. In general relativity, people look at asymptotically locally Euclidean or something like that, or asymptotically hyperbolic or whatever. In which case, the story is actually very similar to the compact case. So I'm going to just talk about compact manifolds. And now a second issue that I want to stress is that we're talking about intrinsic behavior at large scale. So, for example, I'm not concerned with the difference between both of these are circles. Okay, the fact that this one is bent is a manifestation of its extrinsic realization as a subset in the plane. And I'm also not going to talk about things like distances and metrics and curvature, because those are imposed on top of intrinsic topological or intrinsic question about differentiable structure. So by the same token, these are both circles. They're the same as the one above. They differ only in their extrinsic way they appear in 3-dimensional space. One is a unknotted circle and the other is knotted, but that's an extrinsic property, and I won't be talking about that either. If you were an ant and you were living on that circle, you wouldn't, and you couldn't see off of the circle, you wouldn't know the difference. So that's the way we want to think about it. So, and now the question is, I made this assertion that the line and the circle are the only 2 one-dimensional manifolds, and that's a calculus exercise to prove that. And it's also a calculus exercise to show that all one-dimensional manifolds have smooth structures. That is, right. Okay. So let's move on to two-dimensional manifolds. So in two dimensions, uh, there are two infinite families of them. There's the orientable ones, a sphere, torus, two-hole torus, three-hole. So they're labeled by the number of holes, which is called the genus. And so those are the orientable ones. And the non-orientable ones are obtained from the orientable ones by an example of a construction I'm going to indicate later, which is surgery. So what you do is you cut out, you take the Mobius band, which is the kind of fundamental non-orientable two-dimensional space, and it has a boundary. The boundary of the Mobius band is the circle, so you go around it. And it's just a single circle, and the first of the two-dimensional manifolds is cut a little disk out of the sphere. The rest of it is a disk, and you attach that disk to the boundary by just gluing a circle to the circle. And then, so that's called the projective plane. And then you can get what's called the Klein bottle by taking a little disk out of a torus, and its boundary is a circle there. And you take that circle and you glue it onto that circle by some one-to-one map, and then you get the Klein bottle, and then you get higher genus Klein bottles, and so on by doing each of these cases. So those are the two families of the one is what are called or the orientable family, the other is the non-orientable family. So a little quiz. So remember I made this distinction between uh, um, extrinsic and intrinsic behavior. So this is an example. Pretend it's not touching in the middle. So there's an intrinsic example. So which of the manifolds on my list is this one? Okay, so this is one of the manifolds on my list. The boundary of this pretzel, whatever it is. So which is it? So we want to ignore its extrinsic embedding in R3. So this actually brings up a key point, which is, again, I'm not interested in, can't seem to get that to work. I'm not interested in extrinsic properties and metric properties. So from point of view of what I'm talking about, the size has no bearing here. These are all the same. They're actually they're all two-hole tori. If you were guessing correctly, the pretzel is a two-hole tori. So I'll say a little bit about this maybe at the end if I have time, but a proof that these are the only compact connected two-dimensional manifolds. The one-dimensional case was proved by calculus. This two-dimensional case, you can construct a proof using the Riemann mapping theorem. So and I'll say a little bit more about what that is at the end if you haven't seen it, but it's complex analysis. So you use theory of complex functions, functions of x plus iy, to prove that those are all the surfaces in the list. And as was the case with one dimensions, every two-dimensional manifold has an essentially unique smooth structure. And what that means is in practice, and I'll say more about it, is that any two with the same genus, for example, orientable ones, can be identified by an invertible map that identifies a set of infinitely differentiable functions on one with a set of infinitely differentiable functions on the other. If it had two smooth structures, you would have two disjoint sets of functions, which for all practical purposes, you would be able to call infinitely differentiable. So you'd have two sets of functions, two different ways of taking derivatives. And there would be no one-to-one invertible map that identified one set with the other. Okay, so let's talk about three dimensions. So if we move on to three dimensions, first of all, three dimensions, we live in three dimensions, but we only see basically a local region. So we think three dimensions is kind of flat. You think of a coordinate grid. So we need a way to think about three dimensions. So the first illustration is depicting the three-dimensional sphere. So I want to do that. If it works here. Somebody puts it down at the bottom. So three-dimensional sphere is the set of points in four space, x1, x2, x3, x4, whose distance from the origin is equal to 1. So if you want to depict that, you start with a solid ball in R3. So just think of the apple with its inside, or basketball, or soccer ball, or the earth, but the solid, not just the boundary. And so that's going to be a depiction of the northern hemisphere of the three-dimensional sphere, the part where the fourth coordinate is bigger than 0. So this interior of this is a manifold, a three-dimensional manifold, and then it has a boundary. The boundary is the two-dimensional surface. So if you want to depict the three-dimensional sphere, what you can do is you can take two copies of this ball, solid ball. One represents the northern hemisphere of the three-sphere, the other represents the southern hemisphere, and the two northern hemisphere and southern are glued on their boundary, which is a two-dimensional sphere. So the way to depict the three-dimensional sphere is to take two solid balls and think of an identification between their boundaries. So the analogy is obtaining the two-dimensional sphere by cutting it on the equator, and the top part is just a disk, and the bottom part is just a disk, and you're just identifying the two disks on the equator. So here we're taking the three-dimensional analog of a disk, which is a solid ball, and another solid ball, and we're identifying them. On their boundary, the boundary is now a two-dimensional sphere. So what is that? How do you depict motion in that two-dimensional sphere? Well, the idea here is that if you were to start, say, in the North Pole, in the northern part, and you start walking and you get to the edge of the northern half, then you're on the boundary. What happens is you immediately, as you cross, you don't cross the edge, you immediately appear on the other side and come here. So path on the three-dimensional sphere would go from here to here, and then it would immediately reappear over there. So this is, again, a manifestation of the fact that the three-dimensional sphere can't be covered by a single coordinate chart. You need two charts, and this ball is the first chart, and that ball is the second chart, and as you leave this chart, you enter that chart. Okay, now second example is the case of product S1 cross S2, a product. A product space is a set of points, pairs of points. First point is in the circle, second point is a point on the two-sphere, which I label with latitude and longitude. Or longitude and latitude, I forget. But anyway, so it can be depicted in this way. Take a ball and cut out a solid ball, cut out another littler ball inside. So imagine you had comes to my mind is you have a peach, right? And inside the peach is a pit. So somehow take the pit out without ruining the peach. Then you have a solid part and then empty region in the interior. And what you do is you identify the boundary of this region, which is a two-dimensional ball, with the boundary of the outer boundary. So this radial direction is the circle direction. So you start on the inner boundary and you start walking out radially. And when you get here, you don't exit, you end up coming back into the inner boundary because you identified the two. So that's how you depict S1 cross S2. And a second iconic manifold is the three-dimensional torus, which is a product of three copies of S1. And here it's the gluing is you take a cube and you identify the bottom face with the top face, right face with the left face, front face with the back face. And this is the analog of taking a piece of paper and identifying the top and bottom and front and back to roll it up to get a torus. So this is a three-dimensional torus. Again, if you started here and started walking up in this direction, you got to the top, rather than exiting the cube, you just reappear at the bottom again. Or you start here on one side and you start walking to the other side. Instead of exiting the cube, you just reappear on that side. Now, so those are three simple manifolds, but there are much more complicated ones that you can construct. And one way to construct it is consider the three-dimensional sphere, which I represent as just two solid balls again. You can take a knotted circle in one of the sides, and what you do is thicken up that knotted circle. So think of it as an actual piece of rope or bicycle or a knotted piece of rope in the. So we just focus on one side. And so the boundary of this knotted circle is a torus. Going around this direction is the theta direction. Going around the long way around the knot is the phi direction. So that's just a solid torus. And what you could do is you can take that torus out. So this is another example of surgery. You can take it out and glue it back by identifying the coordinates in a different way. So, for example, theta on the inside gets identified with theta on the outside by some linear combination of theta and phi. And likewise here, these A, B, C, Ds have to be integers because theta is only defined up to multiples of 2 pi. And they have to satisfy this rule AD minus BC equals 1, so that what you're doing is a one-to-one identification. So in general, this will give you a new three-dimensional space, not the original one. And when you do that, and that new three-dimensional space will depend on your choice of A, B, C, D in general, and it will also depend in general on the knot. And of course, you could take more than one knot and do it, and the knots could be linked together, and you can take some very complicated link and do this with different ABCDs on different links. So you get a whole plethora of three-dimensional spaces. By doing that, and actually there's a theorem that any three-dimensional space, compact, connected, can be obtained from some link by doing these constructions. Now, an important point is that you can get the same three-dimensional space by taking different knots and different ABCDs. So this is one way to construct lots of them, but it isn't, for example, a way to give a list of three-dimensional spaces because your listing knots and ABCDs will be redundant. Okay, so so it turns out, as I said, that you're getting more, you're getting all of them by doing that, but you're getting many of them multiple times. So by the way, are there any questions? If you have a question, just speak up here. I don't want to. Okay, so fantastic theorem was proved around in the 2000s, which is called the geometrization theorem. And this was conjectured, and a good part of it, well, anyway, part of it was proved by Bill Thurston, who did this kind of fundamental work on it in the 1980s, early 1980s. And then the proof was completed in a rather, remarkable series of papers by Gregory Perelman in 2002, 2003. And the statement of the geometrization theorem is it says any compact orientable three-manifold can be uniquely decomposed along either two-dimensional spheres or two-dimensional tori. So you can cut it on spheres and tori, and these spheres and tori are essentially unique, so that the resulting parts have one of 8 possible structures, and those structures are geometric structures, actually, modeled on hyperbolic spaces and spheres and stuff. But anyway, 8 possible structures, and what that says is that there's some 8 model spaces, and the thing you got after you cut on spheres and tori, each piece is the quotient of one of those 8 model spaces by the action of a discrete group of isometries. So it's a rather a remarkable theorem. And so what happens is basically it reduces the question of understanding 3 manifolds to question of group representation theory, basically. Um, so Perelman's proof is built on the fundamental work of Richard Hamilton regarding a differential equation. And so this differential equation that Hamilton invented and studied is called the Ricci flow equation. And what it does is you put a Riemannian metric on the 3 manifold, and of course there are infinitely many possible choices. But you put a metric on it, and then you evolve it according to time by this equation. This is the time derivative is minus twice the Ricci curvature of the Riemannian metric. So the metric is a symmetric two-dimensional tensor, and the Ricci curvature of a metric is part of the curvature tensor is also symmetric. So this equation makes sense. And it's a very nonlinear matrix incarnation of the heat equation, which is just a time derivative of a function is Laplacian, the sum of the second derivatives of the function in the different coordinate directions. So that's the heat equation. So Hamilton started studying this equation, and he proved fundamental theorems that said, the idea here is that the metric, and this Hamilton's, work was completed by Perelman, or Hamilton's idea here was completed by Perelman, and the fundamental idea here is as the metric flows, it decomposes the space, it finds these 2 spheres, it finds these tori, and it puts on what's left, it puts on these special geometric properties. So each one of these eight possible model spaces has a very special Riemannian metric. And this flow finds, converges in a sense to those special Riemannian metrics. So this is kind of beautiful work, and just put it mildly, the analysis is quite formidable. But anyway, it's a beautiful kind of end of the finishes the 3-dimensional story. And one of the implications is what's called the Poincare conjecture, which is a famous conjecture in topology, that there's a unique, simply connected 3-dimensional manifold, which is the 3-sphere. And another thing, again, kind of a aside here, 3-dimensional manifolds all have unique smooth structures, so that actually is not easy to prove, and I don't even know if I understand the proof of that. But anyway, they have unique smooth structures. Okay, so before we go to 4, let's go to 5, 6, and higher. And so kind of an interesting fact here is that the classification in dimensions 5 and above was known in the 1960s. The question was reduced to questions, sometimes quite hard questions in algebra. But the story was worked out in the 60s by various people. Steve Smale, was the central figure here, Stallings, Milner, Rob Kirby, others. So from regarding smooth structures, one aspect is, this came from the work of Kirby and Siebenmann, that whether a manifold has actually a smooth structure, that is, whether you can actually put on it coordinate charts which have differentiable transitions between them, is determined by a Z2 valued invariant, a +1 or -1. If it's +1, you can do it. If it's -1, you can't do it. So, and then there are examples of manifolds with -1s. So there's just one invariant called this Kirby-Siebenmann invariant, which detects whether the manifold in dimensions 5, 6, or higher. And then another theorem in these dimensions is that any given manifold in dimensions 5 has only finitely many smooth structures. And a rather beautiful theorem in the 1960s by John Milner and Curvaire and other people involved is you can list now what are the smooth structures on the spheres. So take a sphere, n-dimensional sphere is the round set of points in Euclidean space of dimension n+1 with distance 1 from the origin. And then you can compute the number of exotic structures, smooth structures. So of course there's a standard structure, just looked as the sphere in Euclidean space. So there's a unique one in dimension 3, that's Perelman's theorem. The unique in dimension 2, as I said, that's the Riemann mapping theorem. There's unique in dimension 1 is calculus. We'll get to dimension 4 in a minute. Dimension 5, there's only one. 6, there's one. And 7, there's 28. 8, there's 2. 9, there's 8 of them. In dimension 10, there's 6. 992 in dimension 11. Dimension 12, there's just one, and so on. And so these are related to Bernoulli numbers, those famous combinatorial numbers. But anyway, you can do the computation. So it's remarkable. And actually, Milner's paper on the seven sphere is a beautiful paper. And if you have a chance, you should look it up and read it. So interesting fact is that this 5 and plus dimensions was done in the 1960s and 3 dimensions only in the 1980s. And the reason is that the technology for doing 5 and above is very different. It's not really analysis anymore. Whereas a dimension in 2, 3, 1 was of course classical, and 2, probably 1900s, I don't know, 1900. And 3 was only done in the 1980s, but 5 and 6 and above was done in the 1960s. That was Smale's theorems. Okay, so what about dimension 4? Which is the dimension we live in. What can we say about dimension 4? So first of all, it's hard to visualize 4 dimensions. We think of it as space plus time. Time increases, things change in space. We think of it as kind of a movie. The point is really hard to visualize 4 dimensions without practice, because we're somehow genetically imprinted. It makes it hard to travel in time, say into the future. But some people can do that. And for example, magicians, there's some magic tricks like card tricks. So for example, a magician would say, pick a card, and then you pick the card and the magician says, don't show me, then put it back in the deck. The magician shuffles the deck and then picks out your card, right? So how does the magician do that? Well, the magician traveled forward in time to the point where you were picking the card and then was standing behind you, saw the card, instant, was just behind you for a fraction of a second, saw the card, then went back to its own time, and then so actually knew the card you were going to choose before you even chose it. So that's how the trick is done. And if you ever go to a magic show, you'll know when the magician is doing that, because when the magician appears in your space for that fraction of a second, almost the blink of an eye, that displaces a certain amount of air. And when the magician leaves, the air comes back in, there's a little clapping noise. So you will, if you pay attention, not, of course, the magician is trying to deceive you and make you look the wrong way. But if you pay attention to what's going on, you'll hear that little clapping. That'll tell you the trick.
Cliff, have you mastered this card trick in this way?
Yeah, I can do it. If you come to my office later today, I'll do the trick for you.
Okay.
I'm not very good at it. There are people, of course, who are much better at it. But anyway. Okay, so anyway, in 4 dimensions now, so we see in 5 and higher, we have to worry about smooth structures, and we're not. And if you're not worried about smooth structures, you don't care about a smooth structure. So you basically don't want to do any physics at all. Then up to except for there were these monumental works by Mike Friedman, based on some really early clever work by Andrew Casson and Bob Edwards, that classified a good set of manifolds in dimension 4. Their classification hasn't been completed only for manifolds which have very complicated fundamental group, and I'll tell you a little bit about what that is. But anyway, for basic 4 manifolds, for all the ones we're going to be talking about, this work by Mike Friedman. And so in particular, there are a special group of 4 manifolds are called simply connected. Simply connected means that if you have a loop at a given base point, you can pull that loop in continuously contracted loop, so that the loops can't get hung up on stuff. So lots of examples of simply connected ones. And for those cases, the Friedman's theorem says that basically the topological, so non-smooth, we're not worried about 4 manifolds, topological 4 manifolds are basically determined by a set of equivalence classes of 2-dimensional spheres, maps of 2-dimensional spheres into the manifold. So how can the 2-dimensional spheres get hung up? And this turns out to be algebraic data, which consists of an abelian group, just some number n possible with integers. So n copy n different integers, a group named this group, and then on that group there's a symmetric bilinear form, which is called the intersection pairing, and that's an integer valued bilinear form with determinant 1. So you specify basically the number n, which is the rank, and then you specify this bilinear form with determinant 1. And of course, the bilinear form is only well-defined up to change of basis. So you have to take that into account. But up to change of basis, you're given the rank n and the bilinear form with determinant 1 and integer entries. And then there's one other piece of data in the case where that bilinear form has an odd entry on the diagonal. And that extra data is a +1 or -1. And that actually is a kind of a 4-dimensional analog of that Kirby-Schiemann invariant. because if it's a -1, then the manifold can't have a smooth structure. Okay, and conversely, if you have an integer n in a bilinear form and that extra plus or -1 when there's an odd entry on the diagonal, then you can construct a manifold with that data. So Friedman's theorem completely solves the classification problem. And so, for example, if you're not worried about smooth structures, Friedman's theorem says there's a unique four-dimensional sphere, because then n is 0, there's every two-dimensional sphere is contractible, and then the q is just the 0. There's no q to talk about. So this is the four-dimensional Poincare conjecture in the topological category. You don't worry about smooth structures. Another example is complex projective two-space, which is the space of complex one-dimensional subspaces in 3-3, C3. It's a smooth four-dimensional simply connected manifold with n equal 1, so it's just one rank 1. And so Q is just a number, which is 1. And Friedman says there are just two manifolds with n equal 1. If you're not worried about smooth structures, one does, which is that CP2 I just described, and the other doesn't. The other is called the Chern manifold. So presumably, if you're doing physics or you're doing gravitational path integrals, you don't care about the Chern manifold because it doesn't have a smooth structure. Although maybe you do, I don't know. Nobody knows what quantum gravity is in 4 dimensions, so maybe you do. Another example is S2 cross S2, product of two spheres, point in one. So you're looking at pairs of point in one sphere, point in the other. Friedman's theorem says that if you don't worry about smooth structures, there's just one of them with n equal 2, and its q is the off diagonal. So in other words, a two-sphere across a point is one, and a point across a two-sphere is the other, and this tells you how they intersect. So if you don't worry about smooth structures, one S2 cross S2. On the other hand, if you look at the diagonal q with n equal 2, which is not equivalent to this one over the integers, because this one has odds on the diagonal and this one only has evens. Then there are two versions of that. One is what's called the connect sum of two copies of CP2, and the other is, involves a Chern manifold. So what is the connect sum operation? Anytime you have two manifolds, could be 4 dimensions, any dimension, same dimension A and B, you take out a ball from A, another ball from B. Their boundaries are respective spheres in one less dimension, and then you just identify the two spheres together like that. So for example, any genus G surface can be gotten from a genus G minus 1 surface by connect summing with the torus. So that's okay. So what about smooth four-dimensional manifolds? So you guys know Bob Dylan. You guys may be too young to know about Bob Dylan, but anyway, Bob Dylan, famous singer from the 1960s. Anyway, it's a complete unknown. That's Bob Dylan's famous phrase. We don't know well, we know a lot more than we did 20 years ago. We know a lot more 20 years ago than we did 20 years before, but we still don't know anything, basically. So whereas our knowledge seems to be increasing at a steady pace, the amount of ignorance, we don't seem to have made a dent in the amount of ignorance. I don't know. Maybe other people will have a different opinion, but let me just summarize. So there are manifolds that are not covered by Friedman's theorem, namely that their intersection form doesn't have an odd on the diagonal, or the invariant is +1. that do not have smooth structures. So this is big theorem of Simon Donaldson. So there's a conjecture called the 11/8 conjecture, which says that when Q is even, the ratio of this rank n to the signature, if it's bigger than 11/8, it can have a smooth structure. Okay. So for example, Donaldson's theorem says if Q is either positive definite or negative definite, it doesn't have that would be the case. This ratio is equal to, wait, I got it wrong. Maybe it's less than 11. I think I want 8/11. I don't know. I got these numbers wrong. I think I want the ratio to go the other way. Yeah, I got this backwards. It should be less than 11/8. Now I'm totally confused. Anyway, if it's definite, these are the same, and then the ratio is right. Ratio is wrong. So I got these inequalities going the wrong way. They should go the other way. So you conjecture is if the ratio is less than 11/8, it can have a smooth structure. It's known that if it's less than 10/8, it can't. And that was worked out by Amikio Furuta, and actually slightly better estimates have come in recently by some students from here working with Mike Hopkins. So even the Kirby-Siebenman invariant isn't the whole story in dimension 4. There's this 11/8 conjecture. So on the other hand, it's also known in dimension 4 that there are smooth compact manifolds with countably infinitely many distinct smooth structures. And I'll give you a construction. I'll illustrate a countably infinite family of them in a moment. Right. And in fact, there is no compact four-dimensional manifold which has a smooth structure where we actually know what the list of smooth structures are. So there's no case where it can be said we know the whole list. So there's no viable conjecture either, I don't think. I mean, I once made a conjecture, so I stopped making conjectures after this, but I once was giving a colloquium talk. I made a conjecture about smooth form manifolds, and somebody in the audience raised their hand and say, wait a second, isn't such and such a counterexample? So my conjecture was disproved basically 2 minutes later. So the point of making a conjecture is that you want it to last for a long time, so it becomes a famous conjecture like Poincare conjecture or something like that. But if you make a conjecture that gets shot down instantaneously, then that's not so good. Okay. So anyway, there's no conjectural list. We don't know any conjectural list. So as far as we know, we only know one smooth structure on the force sphere, which is the round force, one that comes from viewing it in as a boundary of the ball in five-dimensional space. We only know one on S2 cross S2. We only know one on that space CP2. So it could be that those are the only ones. It could be that there are just a whole bunch of them that we just don't know anything about. And so just to give you a hint of how subtle things are in dimension 4 relative to the other dimensions, you can ask, what about Rn? So how many smooth structures could there be on Rn? And so the answer is, I mean, there's the obvious vector space structure, but could there be others, right? And so the answer is that in dimensions not equal to 4, there's a unique smooth structure on Rn. And in dimension 4, there's uncountably many smooth structures on Rn. And so what that means is that uncountably many ways to specify sets of smooth functions on the Euclidean space such that no two sets can be identified by any invertible one-to-one map. And so, which is kind of hard to get your head around, but the interesting thing about these, so if we had a fake force sphere, if we had an exotic force sphere, you could take a point out of that force sphere, then that would be a fake R4. And that fake R4 would be asymptotically flat because the neighborhood of a point just looks like Euclidean space would be, from the point of view of that end of the manifold, it would look like taking a point out of Euclidean space, which is just a 4, asymptotically flat. So if you had a fake force sphere and you pulled out a point, you would get a 4 manifold, which was exotic R4 that had metrics which were asymptotically flat. So I don't know whether that would mess up people's thinking about general relativity or not. But all the ones we know about are asymptotically really, really messed up. And so what that means is that outside of some large bounded set, there's no way to embed a three-dimensional ball. So there's no smooth three-dimensional ball that sort of engulfs a very, very large set. There's, of course, a topological ball, because after all, these are topologically R4, but there's no, in these fake smooth structures, there's no smooth ball that you can put in there. So they're very asymptotically, very weird spaces. So maybe they have nothing to do with physics. But if you had a smooth structure on S4, presumably it would have something to do with physics. So do you guys want to take a break? I mean, I've been going for about an hour, or how should we do this? Or should I just? Right. Okay. So I want to demonstrate some exotic manifolds for you, just so you can see what's involved. So the starting point is what's called a K3 surface, which is the zero locus of, you take C4, 4 copies complex numbers. You look at the zero locus of this fourth order polynomial. If you rescale the coordinates all by the same number, then you're still there. This is a homogeneous polynomial. So you take the quotient by the action of the non-zero complex numbers by multiplication, and you get a four-dimensional manifold. It's a complex manifold, but it's four-dimensional real manifold, and that's called a K3 surface. So that's a famous four-dimensional manifold. It's simply connected so that every loop can be pulled into a point. The rank of that group is 22, and the Q is even Q. It has 19 negative eigenvalues and 3 positive ones. So as a bilinear form, if you're familiar with Lie groups, there's the E8 lattice. So it's 2 copies of E8. These are 8-dimensional negative definite. And then this one, 0, 1, 1, 0, is what you saw for the S2 cross S2 anyway. So that characterizes it according to Friedman's theorem if you're not interested in smooth structures. So Friedman's theorem says it has uniquely smooth structure if you ignore, it's unique if you don't care about smooth structures. If you don't worry about differentiating functions. And it turns out that it has countably many distinct smooth structures. So I'm going to explain how to get at least one countable family of them. As I said, we don't know the whole list, but here's a countable subset. So it turns out that this K3 manifold has a particular embedded torus inside it. and S1 cross S1, whose neighborhood is a product. So I've depicted that this is that torus. The neighborhood is a product, tubular neighborhood is it's normal. There's a normal to that torus is a two-dimensional disk. So as you go around at each point of the torus, there's that normal direction, which has a neighborhood, which is a two-dimensional disk. Okay, so I can explain how to find that. If you know some complex, theory of complex surfaces, you can find where that it's actually a complex torus. Okay, so what you do is you take that torus and you cut out that solid T2 cross D2. So you have that T2 cross D2, the solid thing. I've drawn some of the disks. You cut it out, you get a manifold with boundary, which is just the product of S1 cross S1 cross S1. It's a three-dimensional torus. There's the original two-dimensional torus, and then there's the boundary of each disk, which is the extra S1 here. Okay, so what you want to do is you cut that out and you want to glue in something with the same boundary. So that's our strategy. Just cut something out, glue in something with the same boundary, and then the idea is if you did it the right way, you could invoke Friedman's theorem to see that you got back something which was topologically the K3 surface, but hopefully not the same smooth manifold. So what do you want to glue back in? Well, okay, so you take a knot in the three sphere. I've just drawn one hemisphere, and here's your knot. And you take the complement of that knot. So the complement of that knot has a boundary which is a two-dimensional torus. Of course, the inside of that also has that same boundary, but you take everything away from the knot, you take out the rope, and then you just cross with S1. So the boundary is just this torus, the theta direction and the phi direction. You cross with S1, and then you have something with the same boundary as that. So that's what you're going to glue back in. You take the complement of the knot, cross it with S1, and glue it back in. Now, there are various ways to do that gluing. There's various ways to identify one S1 with the other, and there's a specific way to do it. I won't get into the details, but there's a specific way to do it, which S1 glues to which. But if you do it the right way, you get something which is simply connected. So the fundamental group, all knots can be pulled in, it has the same N and the same Q. So by Friedman's theorem, it is, if you ignore smooth structures, it's the same manifold. So there's a theorem due to Ron Fintussel and Ron Stern saying that the result is not the smooth K3. It's an exotic differentiable structure if you choose a knot which has non-trivial Alexander polynomial, and I'll say what that is in a minute. And moreover, two knots with different Alexander polynomials give you distinct smooth manifolds. So here's some examples. The unknot has Alexander polynomial 1. So the Alexander polynomial is a polynomial in a variable t and t inverse. Okay. The unknot has no t, it's just the constant 1. The trefoil knot is this polynomial. The figure 8 knot, which has that polynomial. So these are invariants of knots, which says that if you move the knot in three-dimensional space, but don't do any crossings, you get the same polynomial. You can't change the polynomial without having strands cross each other. So if you took the trefoil knot, according to Fintussel and Stern, and did this construction where you cut out the inside of the rope, cross with S1 and glue it to that, you would get something which was, according to Friedman's theorem, the K3 surface, if you don't care about smooth structures, but actually in terms of a smooth structure, it's different than the original K3. If you did it with the figure 8 knot, you would get something different from the Alexander one and different from the standard one. So here you would have 3 different smooth structures on K3 by doing this ventricial stern. It's called knot surgery, ventricial stern knot surgery. So let me say something about the Alexander polynomial. There's a way to compute it if you depict a knot. So here are 3 depictions of the standard circle, unknotted circle. I've just kind of shown they're all unknotted. You're given a picture of this called a projection of the circle, a projection of the circle onto a plane. You can compute from the crossings. This polynomial is a rule for computing it, and I won't split the rule, but you can look it up. It's not that complicated. So the only constraint on the Alexander polynomial, it has to be a polynomial in T and T inverse. Its sum of the coefficients should equal either 1 or -1. And it should be symmetric. That is, you switch T with T inverse. It doesn't matter. And any such polynomial is realized as the Alexander polynomial of some knot, actually more than one knot, usually. It doesn't completely distinguish knots. It's only partially. So there are infinitely many possible different Alexander polynomials. So there are infinitely many different smooth structures on that K3 surface. So here's where we are at the frontier, okay? So this is the frontier of our knowledge about K3 surfaces. So this is a knot called the Kinoshita-Terasoda knot. And its Alexander polynomial is just constant 1. It has no T. So it's the same Alexander polynomial as, oops, where'd I go here? Same Alexander polynomial as, didn't mean to do that, oh well. As the unknot here is this guy. So, oops, X. So this and this have the same Alexander polynomial. So it's not known that if you did knot surgery with this guy, do you get an exotic K3 or do you get the same as you would get if you did this one, where you get the standard K3? So that's kind of the boundary of our knowledge, whether if you used the standard knot or this Kinoshita-Terasoda knot, whether this gives you something exotic that we have no way of knowing, because the only if 2 Alexander polynomials are the same, we have no other way to detect the exoticity. So that's the frontier right there, is whether these 2 knots give you the same format. Okay, so how did this Alexander polynomial show up? Well, I'm going to just say a word about it. So there's how they are distinguished. This was a brilliant idea, which was invented, I guess, by Simon Donaldson, which is you take solutions to some standard iconic equation. So you put a Riemannian metric on your manifold, and for example, you can write down the self-dual Yang-Mills equations or your Seiberg-Witten equations, and then you count the solutions with a plus or minus weight. The plus, and you can't count absolute numbers because the number of solutions might change as the metric changes. I'll say more about that at the end, but if you're clever about how to assign a 1 and a -1, then solutions appear and disappear in plus -1 pairs like they were particles and antiparticles, annihilating until your count doesn't change if you change the metric. So you put on a metric, you count solutions to your equations. If you count them algebraically in a clever enough way, you get the same count no matter what metric you choose. And so therefore it doesn't depend on the metric. It only depends on the smooth structure. And that gives you an invariant, which turns out in these cases to be basically the Alexander polynomial of that knot. Okay, so what about the force sphere? So there are, as I said, Friedman's theorem says that if you don't care about smooth structures, there's just one, but if you care about smooth structures, actually potentially there are lots and lots of ways to construct four exotic force spheres. It's not like we don't have any possible counterexamples. The problem is that we don't have any way to tell that these constructions don't actually give you the standard force sphere back. So there's a recognition problem. How do we recognize when something is exotic when you can only see local behavior? So the conjecture, which actually probably nobody really believes or nobody would bet a whole lot of money on, is that the force sphere has just one smooth structure. This is known as SPC4, the smooth four-dimensional Poincare conjecture. And in some ways, this is kind of the last, big conjecture or overriding conjecture in smooth manifolds is this smooth four-dimensional Poincare conjecture. Okay, so what I'm going to describe is a promising method to construct exotic force spheres, which would disprove his SPC4. So the paper was first, the idea was, it's not a very complicated idea, but it was first described. Well, actually, it is. I mean, it's clever. I mean, I don't want to say it's not. I wouldn't have thought of it. But anyway, it was described in a paper by Mike Friedman, Bob Gompf, Scott Morrison, Kevin Walker. Famous paper called Man and Machine Thinking About Smooth Four-Dimensional Poincare Conjecture. So they wrote this paper, and I'll explain. It's kind of a little irony about that, which I hope to explain later. But anyway, their suggestion kind of languished for about 10 years. And then it was picked up and greatly expanded and formalized in a very influential paper by Lisa Piccirillo and Ciprian Manolescu. So, Lisa and Ciprian sort of evaluated what they did and saw sort of a general way to view it, and so now it's a lot of people kind of thinking about that. Okay, so how does it work? So I'm going to try to describe this to you schematically. You start with the round force sphere. So here's the northern hemisphere. There's the southern hemisphere. So think of the force sphere. Okay. So the northern hemisphere, so we look at force sphere as a set of points in R5 with norm 1. The northern hemisphere would be where x5 is bigger than 0. The boundary where x5 is equal to 0 is the round 3 sphere. So we think of that as the boundary. Okay, so in that boundary, the boundary is just a 3 sphere. We take a knot. So we're going to, again, everything seems to depend on knots. Take a knot in the boundary, take the solid tube, again, centered on that knot. Think of it as a thickened knot. You have a direction theta, direction phi. And the solid neighborhood is just a product of a circle, which is the knot, and then the solid tube around it is discs. So here you have the discs, and here you have the circle. So this is same drawing I had above for that torus. But now we have a knot in the 3 sphere, and then the solid part like that. All right, so what you want to do is you attach to the boundary you attach to the boundary. So if you look at the product of two disks, a D2 cross D2, one of the disks has boundary S1, but think of this as S1 cross D2. That's the boundary of D2. Well, it has two boundaries, parts. One is this S1 cross that D2, the other is this S1 cross that D2. But just take this part of the boundary, S1 cross D2, and identify that S1 with the phi direction in this knot going around, and just glue that solid D2 cross D2 onto take the top half of the force sphere with the knot in the boundary, and then you glue this solid D2 cross D2 onto the D2 S1 cross D2, which is the knot, thickened knot. So we're not taking that thickened knot out, we're just using it as the gluing region. It's the part where you have a tube of glue and you're putting the glue on that. You're putting the glue on this S1 cross D2. So you kind of smear this with glue, and then you attach this four-dimensional thing, D2 cross. So now you have something which has a new boundary, its original boundary S3, but then you've attached that onto it. So that's called the trace of the knot. It's called a zero trace, actually, of the knot, the zero trace. Okay. So if you're following that, we took the northern hemisphere, we had a knot in the boundary, we attached a D2 cross D2 by gluing this part of its boundary to here and here. The rest of its boundary makes up the boundary of the thing original boundary was a three sphere, but now we have something different because we have a new part of the boundary like that. Okay, now a knot in the bound. So now hold on to this trace for a minute. So if you're looking at a knot in the boundary of S3, it's said to be a slice knot. So there's the word slice knot. If it actually bounds an embedded disk in one of the hemispheres. So a knot in S3 in general will bound an immersed, some, kind of self-intersecting disk. But special knots are called slice knots, where they actually bound a disk that doesn't intersect itself. So those are called slice knots. By the way, it's not, we'll see in a minute, slice knots play a role. So for example, the trefoil knot, I think, is a slice knot, whereas the figure eight knot is not a slice knot. Okay, so this one, if I think of it as a knot on the boundary of the four ball, actually bounds an embedded disk in the four ball without self-intersections, a smooth two-dimensional submanifold. This one does not. There's no embedded disk without self-intersections. It can't be embedded. That has boundary, the figure eight knot. So we have these two knots. One of them is sliced, the other one isn't. Okay, now if it's a slice knot, then this knot trace is actually a subset of the force sphere, because that disk, that D2 cross D2 is just a neighborhood of that slice disk. So if you had a slice knot, your trace, that knot trace, which is the upper part union this, actually sits inside the force sphere. Okay, if it's not a slice knot, that presumably doesn't sit inside the force sphere, but if it is, you can actually see the trace as something inside the force sphere, as a submanifold in the force sphere with boundary. Now, so here's the idea. Suppose you have two knots, A and B, and we suppose that A is a slice knot and B isn't a slice knot. So suppose A is and B isn't, but suppose their traces are actually smoothly identified. They're the same smooth manifold. And what Manielecki and Piccirillo did was give conditions whereby you can generate pairs A and B. Well, given an A, you can generate a B such that their traces are the same. So two different knots whose traces are actually the same four-dimensional space. So if that's the case, what you can do is you can take the trace of B, which doesn't sit inside the force sphere because this neighborhood of the slice disk, this neighborhood of this D2 cross D2 doesn't sit in the force sphere. You can take that trace and you can delete the slice disk from A and you get the rest of the force sphere. You can glue that onto here. All right, so I depicted that below. Okay, so you take the part, this B, this trace of B, which doesn't sit in the force sphere, because B is by assumption not a slice knot. And then you can take the complement of the slice part of the A, because A is a slice knot, so this is part of the force sphere, and you can just glue that to here along their boundaries. And then Friedman's theorem is that that's, if you're not interested in smooth structures, that's going to be a four-dimensional sphere. And if you're interested in smooth structures, it's going to be exotic because by construction, B bounds that disk in this four-dimensional manifold. It's this disk here, whereas by assumption, B does not bound a disk in the force sphere. So you have a knot which bounds a disk, which doesn't bound a disk in the force sphere, but it does bound a disk in this other force sphere. So the other force sphere can't be the standard force sphere. So that's the idea. Find a knot, do this construction. So what you need to find is two knots A and B with A slice knot, B not a slice knot, and with their traces being smoothly equivalent. And if you can do that, then you've constructed, I think, I understand Piccirillo and Manielecki's paper, then you've constructed an exotic force sphere, a different smooth structure. So what people have done is you find, well, first of all, it's not easy to prove a given knot is slice, but anyway, actually, there's a paper on the archive last week where people looked at some, like 20,000 knots or 100,000 knots with less than 20 crossings and found all the slice knots. And then you want to find a B knot, which is not a slice knot, which is equivalent to A knot. Anyway, it's a formidable task to do that. And Piccirillo and Manielecki give you many A's and B's, which are known to be equivalent. But you need to know one is slice and one isn't. In all the cases we know of, we only know the cases where they're both slice. So it could be it's always both slice, and then this construction would never work. But if you found a pair where one is slice and the other isn't, with equivalent knot traces, then you would be in business. So that's roughly, I don't want to say I got all the details here, but that's roughly the construction is you find a knot in the boundary, which is slice in some topological force sphere, but not slice in the standard force sphere. And then you know it can't be the standard force sphere. So that's the way people are working on it. And as I said, there's a great industry trying to find A's and B's. But so far, at least as of this morning, when I looked on the archive, nobody put up a paper that claimed to do that. So But who knows? Maybe tomorrow we'll have exotic force fields, or maybe we'll never have exotic force fields, at least by this construction. Okay, questions. So maybe I should say a little bit why 4 dimensions is hard. So topological constructions in 4 dimensions, the Smale's theorems and a whole above 4-dimensional constructions are based on a simple fact that 2 plus 2 is equal to 4, which is less than the dimension. So the idea here is that if you take two generic 2-dimensional disks in a manifold of dimension bigger than 4, they won't intersect because you can always move them. There's always an extra direction to move them off each other. Whereas in dimension 4, if you took two generically embedded disks, they're going to generally, one disk might intersect itself, and it might intersect a second disk. So, and you couldn't get rid of these intersections by any local move. You'd have to somehow move it globally to cancel the intersections. So these intersections obstruct various ways of simplifying a depiction of a manifold to compare it with another. So why does Friedman's theorem work? Well, Friedman and Andrew Casson had this really brilliant idea, which if you don't require differentiability, what you can do is you can force these intersections into ever smaller regions in the space. So you start out with a disk that self-intersects, and you kind of move the intersection point further and further down. And eventually, again, this is just a caricature of what they do. I mean, it's nowhere near this simple, but the idea is you can put all the bad intersection, all these obstructing intersections, you can put them all around a single point, at a single point. Now, the result of doing that is a space which is not differentiable at that point, or a surface which isn't differentiable at that point. But it's nonetheless, and this is kind of an amazing theorem of Friedman using Bob Edwards' work, that the space is sort of topologically a manifold at that point, even though it's not differentiable. So the idea is you just crowd everything, you push everything into a point, and you give up the differentiability because you put all this kind of complicated junk, you squeezed it into a point, but so the neighborhood of this isn't going to be differentiable. It's not going to be differentiable, but it's still topologically good. And so you get a theorem about topological manifolds that isn't, but it doesn't say anything about smooth manifolds. So that's kind of roughly what Friedman and Casson and Bob Edwards' work does, at least, to a first approximation. Okay, so that's kind of what goes. So you can ask, what about metric constructions? So in 3 dimensions, people use the Ricci flow, Perelman's theorem. In 2 dimensions, you can also use the Ricci flow and prove the uniformization, prove the theorems using the Ricci flow actually in 2 dimensions. But these rely on the fact that the Riemann curvature tensor is determined by the Ricci tensor in 2 and 3 dimensions. There's no extra components of the Riemann curvature. In dimensions 4 and bigger, there's also the Weyl curvature part, which is in Minkowski space why we have gravitational waves. Okay, so this fact makes it problematic to use the Ricci flow to obtain some kind of canonical geometric structure, because First of all, even if you knew what the Ricci tensor was doing along the flow, you'd have to figure out what the rest of the curvature tensor was doing. And maybe that's just becoming totally pathological. So it makes things a lot harder, maybe not even doable, but anyway. So for example, if you state the standard round metric on the force sphere is an Einstein metric, but it's the only Einstein metric we know on the force sphere, but it may be there are infinitely many Einstein metrics on the force sphere, whereas there's just a unique one on S3 and S2. Even so, there's a lot of really interesting work on the four-dimensional Ricci flow, a very active area of research. And a person who's done quite a lot of that is Richard Bamler, who's at, I think he's at Berkeley. And so, it might work out that they can really um, uh, prove some interesting things. So, for example, they have a proposal to prove the 11/8 conjecture using the Ricci flow. So the idea would be to somehow characterize what happens. Okay, so what about so what goes wrong? What about analysis in dimensions less than 4? So analysis, you're looking at differential equations like the heat equation or Laplace equation. These kind of suffer from the same, there's the rescaling inequalities that really are the same inequalities that determine that an interaction in a quantum field theory is either super renormalizable in D less than 4 or not renormalizable, non-renormalizable in D bigger than 4. And in D equal 4, maybe it's renormalizable or maybe not, but it depends on this sort of algebraic structure. And that's kind of exactly what happens when you try to understand differential equations. For example, say a little bit more Seiberg-Witten or Yang-Mills equations. But anyway, it makes it problematic to use differential equations in dimensions bigger than 4 because, these same inequalities that mess up quantum field theories also mess up the analysis in differential equations. So dimension 4 seems to be borderline in both directions. It's borderline in terms of the analysis, and it's also borderline in terms of the kind of moving things around, the hands-on topology that worked in dimension 5. So I don't know if those two facts, it's borderline for both, are coincidence, or if there's some deep connection as to why they're both borderline. One is borderline going one way and the other is borderline going the other way. I don't really know if that's just unpleasant coincidence or not. Okay. So let me just say a little bit more about remarks on analysis since I have a few more minutes. So I said that there's a unique, one-dimensional manifolds are either the real line or the circle, and so how would you prove that? Well, when you do that is you want to find a function on the manifold that has nowhere zero derivative. All right, so we're just looking at functions. We have a function of one variable, at least locally, there's just one variable. And we want its derivative to be nowhere zero. So function is a map from the manifold to the real numbers. If its derivative is nowhere zero, then there's a theorem called the inverse mapping theorem, which says it's invertible, locally invertible. So the goal is to find a function on the manifold whose derivative is nowhere zero. Now, in the case of 2 dimensions, the Riemann mapping theorem, what does the Riemann mapping theorem says? It says if you take any domain in the plane, which is simply connected And no matter how wiggly the boundary, well, there's a little bit of a constraint. It can be like a fractal boundary up to a point. But anyway, assuming the boundary is like relatively reasonable, then there's a holomorphic map, one-to-one invertible holomorphic map to the interior of the disk. So that would be your equivalence. It's a one-to-one invertible holomorphic map. So that's what the Riemann mapping theorem says. It finds basically a canonical holomorphic function up to some slight equivalence from any region that's simply connected to the disk. And so that's pretty cool. And I said in 3 dimensions, we're looking at the Ricci flow, which, as I said, Ricci flow is a nonlinear version of the Laplace equation. So here's, sorry, the heat equation. So this is the standard heat equation. And the Ricci flow is just a very nonlinear version of that, where G is now a symmetric matrix. Okay. So what about 4 dimensions? Well, as I mentioned, 4 dimensions, the idea, what succeeded so far, although actually there's some really promising work very recently, but the idea is to make an algebraic count of solutions, put a Riemannian metric on the manifold, write down some canonical system of equations, count the solutions, weight them appropriately algebraically, and then if you did that cleverly enough, hopefully solutions would only appear and disappear in pairs, one pair with weight plus one, the other with weight minus one, so the sum wouldn't change. So I said there's some very different constructions which don't involve differential equations. They're much more algebraic constructions, and it goes by the name Skane lasagna module. And I have been completely unable to get a good answer why the word lasagna appears here. So if you're not a native English speaker, lasagna is a pasta dish that you can get at an Italian restaurant. Okay, so I have no idea why it's there. The only thing I can figure out is that this were dreamed up over dinner at an Italian restaurant. Anyway, I mean, lasagna is good. It tastes good still. Okay, so we have 2 sets of equations where this procedure works. Seiberg-Witten equation that was suggested by Ed Witten in about 1994, the self-dual equations, which were done by pioneered by Simon Donaldson in about 1982 or 3, 10 years earlier, where you count solutions cleverly with these weights and you get an invariant. Now, it turns out there are lots of other equations you could write down, but the problem is you need to know that your solution space is finite. You need to know that what you're counting a finite set. And not only that, you need to know that it's finite along one parameter families of metrics if you have to put a metric to write down the equation, because you need to know the choice is independent of the metric. So for most of these equations, that's really the central analytic question. Are the solution spaces finite? And not only that, are they finite along one parameter families? And so you can rephrase it as saying, suppose you have a sequence of solutions, does that sequence necessarily converge or have a convergent subsequence? So clearly, if it's finite, it does, but that turns out to be a slightly more weaker question, which is what you need to answer. And if that's not the case, there's still, which actually it's not the case for the Donaldson's self-dual equations. It turns out it is remarkably the case for the Seiberg-Witten equations, but it's not the case for Donaldson's equations. But if the sequences don't converge, do they disappear in plus or minus one pairs, or without affecting the count? So you can allow, infinitely many or non-converging sequences if you can show that there's always, two non-converging sequences, one with pluses and the other with minuses. So, there's some weakness here. You can weaken the situation and allow somewhat more pathological behavior if your algebraic count is uh, um, set up correctly. So just to see what the analog is a calculus question. If you have a function on the real line, which is increasing in the negative direction and increasing in the positive direction, and the theorem is it'll only have if its critical points are non-degenerate, it will have an odd number of critical points. In fact, if you count them so that minima are +1 and maxima are -1, then the sum of the counts is always going to be +1. So here I have a parabola, one minimum, so its count is +1. Here I have some really wiggly function, which has 5 minima, but then it has 4 maxima, so its sum is +1. So that's a theorem in calculus that says, and so what happens if you move this function? Well, pluses and minuses might disappear. You might move this branch over to here, and then you'd get rid of a -1 and a +1. Together, you'd still have an odd number. So that's a theorem in calculus. See if I can do that. So for example, you could modify this function so it doesn't have this maxima. So it looks something like that. This whole branch cut off, but then you'd also cut off a minimum. So you always get rid of them in pairs. But of course, if you relax the asymptotic conditions, you can lose that minimum by just letting the minimum slide off to infinity. So here's a situation where if you don't make these asymptotic constraints, you can lose a minimum. And so that's why the question is really, what can you say about the limiting behavior of non-convergence sequences? And this was sorted out by Karen Uhlenbeck in the early 1980s, and Simon Donaldson immediately saw that Uhlenbeck's theorems could be used to distinguish smooth structures, and he made some calculations and saw that indeed that's what happened. So that was like the big event in the 1980s, and Donaldson won the Fields Medal for that. And then in around 1994, middle 1990s, 10 years later, Ed Witten Witten and Seibert wrote down the Seibert-Witten equations, and then Witten realized that, first of all, the solution space was always compact. You didn't have to worry about any sequences disappearing, and that they also distinguish smooth structures. So this was and now there are other equations, as I said, but they don't, so far, we haven't come to terms with the non-compactness of the non-convergent. They all have situations where you have non-convergent sequences, and at present there's no known way to modify or algebraically weight your count or somehow modify the count so that you actually get an invariant. So that's where we are. So the only promising direction are this algebraic approach of Skene lasagna modules, But the differential equation direction, people are working, a lot of people thinking about it, but the differential equation direction a bit. We don't know how to deal with these more general kind of self-duality or Seiberg-Witten equations. So I guess I'll end here.